This is M3Q Destroyer, which is fast and high precision. I'm Raflis, and I'm captain of Leonardoro. This like a normal airship plane, but it has ability to detect and dropping balls to the drop zone.
This is my friend, Ari. And what should you know about Ari is, aside he's an expert in programming, but he used to be my partner at Racing Plane Division 2021. Our designer is Jonathan. He's mechanical engineer and also my partner at Racing Plane Division 2021. He's responsible for design and manufacture. And this is Farid, our brushless DC motor specialist. He has 2 years experience in brushless DC motors competitions. My next buddy is Yepe, which is advanced at electronics and currently developing our electronic speed controller.
And the last is Andra and Diva, which are responsible for non-technical division.
The three axes including X, Y, Z axis have their own polar line such as UAV center of gravity line, UAV center body line, and chord line of UAV's airfoil. M3Q Destroyer cost distributions including electronic components and manufacturing costs. Most of the costs come from electronic components as shown below. In this M3Q Destroyer, we also collect weight and balance data of each part or electronic components into a table. Weight is measured in grams and balance data is taken from chart calculations by using the weight and coordinates of each component on the three axes. Coordinate of the components measured in millimeter by the distance between polar line of each axis and the centroid of the components. For the main body of the UAV, we are using 5mm polyfoam as primary material, plywood as secondary material, and transparent cellophane tape as coating material. To begin with, we apply the transparent cellophane tape to the surface of the 5mm polyfoam board. Then, we cut the coated polyfoam board and plywood into the predetermined shape using laser cut machine. Due to the laser cut process, plywood's fiber often goes out of place, will need to be smoothened using sandpaper. Finally, the preparation is complete, and the main body is going to be assembled using hot glue on each edge of the part. For the wing section, we are using 5cm styrofoam as primary material, carbon strip as wing spar, transparent cellophane tape as coating material. Then simply stick the airfoil-shaped plywood into the 5cm styrofoam that has been adjusted to the desired wing size and slowly cut the styrofoam by following the plywood's edge using hot wire. For better durability, we covered all wing segments using the transparent cellophane tape. For aileron and flap, first we draw where the aileron or flap would be, then cut it. For better movement of the aileron or flap, we cut 45-degree angle on the bottom side where the flap or aileron would contact the wing, and we stick the aileron or flap back on the wing using cellophane tape. For landing skid, it will be placed under the wing on both left and right side, which will work as a cushion to prevent damage on dropping mechanism and camera gimbals. Lastly, for wing to body mounting, we just stick the plywood that has been laser cut on the middle section of the wing using styrofoam glue. The mounting shape is specially made to perfectly fit with the hole on the main body's front frame, while in the back of the mounting, there is a set of holes as placed for a small tube to complete the mounting system. All servo's arm is connected to push rod made by planing the edges of a small non-brittle rod. The push rod is connected to horns that are planted in the part that we want to move, such as ailerons, flaps, and elevator or rudder. These are some videos to show change in flight controller that affect the airplane movement. The UAV has a fairly heavy mass due to its electronic components, so it needs wings that can generate sufficient lift even at low speeds while still having good maneuverability. The semi-symmetrical NACA2412 airfoil is used because it has good low speed performance and excellent lift-drag ratio. Here is the result of airfoil analysis using software XFLR5. And this is force diagram as a result from computer fluid dynamics or CFD's analysis using ANSYS software. We are using locality motor and ready-made motor from T-Motor AT2826 series 900 kV as per of the UAV's main propulsion device. When the throttle is 40%, this motor generates 9.78 Newton thrust, which is expected to overcome the drag from the wing that we calculated before and drag from the other body of the UAV. The UAV's longitudinal static stability is obtained from the response produced by the pitching moment coefficient or CM when the UAV gets the angle of attack from disturbance. From the following graph, it can be seen that when AOA increases, the pitching moment tends to turn positive. Likewise, when AOA decreases, the pitching moment tends to turn negative. The resulting response of CM and AOA led to the longitudinal static stability. Lateral static stability or roll and directional static stability or yaw of the UAV were obtained from the presence of a vertical stabilizer on the wide tail.
For dropping mechanism, we use hot wire to make circle shapes in the middle sections of the wing. Then, add a servo next to each circle to make a gate-like system which able to hold and release the dropping object when needed.
The power source of our UAV is from 4S LiPo battery that is connected to the switch and 80 ampere fuse for overcurrent protection using XT60 connector. The output of the switch is connected to the Pixhawk power module, which powers the Pixhawk Cube flight controller directly, supplying electricity to components connected to the Pixhawk and electronic speed controller or ESC, which also use XT60 connector. 5-volt power of Universal Battery Eliminator Circuit or UBEC from the ESC is powering ailerons, flaps, droppers, and V-tail servos. The signal cable from the servos are then connected to the PWM outputs of Pixhawk Cube. The output of the switch also linked to 12-volt and 5-volt DC-DC buck converter using JST connector. 12-volt buck converter used to power the camera's gimbal using JST connector, while 5-volt buck converter used to power the Raspberry Pi 4 using a USB Type-C connector. Gimbal motors which stabilize the camera are controlled by the gimbal driver and connected using jumper cable. The gimbal driver also connected to the Pixhawk's PWM servo out pin to control the angle of the camera. The camera mounted on the gimbal captured live video and transferred them to the Raspberry Pi 4 using flat flex cable or FFC. It is also powered using the same FFC cable. Raspberry Pi 4 controls the pixel cube directly for dropping the payload precisely to the target using micro USB cable. The Raspberry Pi also helps aligning the UAV with the target by controlling the ailerons using PWM signal from the pixel. Few methods that use in the assembly of electronic equipment are soldering to connect wires with circuit boards, and crimping for training wires with housings in which will connect to a specified electronic pins. Most of our electronics, including the battery, are bound to the chassis using Velcro straps. The Raspberry Pi 4 uses a custom-made 3D printed mount, securing itself, while the gimbal driver is sticking to the plywood using foam tape. The Raspberry Pi mount and gimbal mount are screwed to the plywood, while the plywood is hot glued to the fuselage.
The fuse are used to protect current above 80 amperes, while our specification of electronic speed controller is 75 amperes. And the switch are used to disconnect the circuit from the power source as soon as possible, so the switch must accessible from the outside. If the remote control is shut off, the fail-safe control will override the aircraft, then stopping the throttle and setting elevator in up position and aileron plus rudder to the right position.
For the Mission 1, we use Waypoint mission-based system with autoplane firmware. We tune some parameters to make the flight characteristic of the plane better to complete Mission 1 efficiently. And for Mission 2, in order to achieve an accurate dropping mission, we use a Pi camera connected to Raspberry Pi to detect the dropping target. We also use gimbal to stabilize the footage. After the dropping target is detected, the plane will roll based on the direction of the detected target. To do that, we use the Robot Operating System or ROS, and we use mappers to connect between ROS and the autoplane firmware. We will use the vertical distance between the center point of the camera frame and the center point of the dropping target to calculate actual distance between the plane and the dropping target. We use this formula to get the right distance to drop the ball. We can get the altitude and ground speed data from the flight controller. After the distance calculated and when the error given by the vision matches that distance, the ball will be dropped.
Here are some related data to the flight and mission performance calculation of the aircraft. We also do simulations that are similar to the competitions with 6 trials. We got our base time for the mission 1 in the 5th trial at 43 seconds. On the mission 2, we finally have all balls on the target on the 4th trials. We use Holybro 43 MHz for the telemetry radio instead of 12XB due to lack of availability on local market. We also change our step-down module for wake reduction. For the camera, we are using wide lens camera to increase field of view. We are using black house instead of VGA socket for simpler wire connection. Motor mounting and frame also changed for wake reduction and adjusting new place for the switch. Our wing lock mechanism is changed for sturdier and more precise structure. The maximum thrust of a ready-made motor is 3 kilos, and the maximum thrust of our original motor is 2.2 kilos. Our chassis strength test by making sure the wing can withstand the UAV own weight. The configuration that used in our locality motor is 12 slot and 14 poles. The stator is made by cutting the plate using plasma cutter. The cutted plates are assembled into a complete stator core. Then, we wind the stator core using enameled copper wire. The motor frame and rotor core are made by CNC method. Then, neodymium permanent magnet is installed to the rotor. After all parts are assembled, we did a no-load test to know the constant RPM of the motor. Here are our remote design and printed using 3D printers. This is our schematic of our ASU.